During this webinar, we speak a lot about microcracks, but in fact, there's many other type of defects that can be found when using EL imaging. For the sake of simplicity, we will just call it microcracks. The thing about microcracks is that they cannot be seen with the naked eye, but they can be made visible using electroluminescence imaging, or EL imaging. For excellent performance, it's critical that all these connections are functional, so your generated electricity can flow without interruption.
High-resolution EL images are being uploaded, and while that's happening, the software starts analyzing, and defects are automatically marked.
Hello everyone, good morning or good afternoon. Welcome to this webinar. Today we will talk about the mass detection of cell inherent defects with the use of our software. This webinar has only been organized last minute and we have over 150 people I see who signed up. So I'd like to welcome everybody. For those who don't know me yet, my name is Benoit van der Maas and I'm International Business Development Director at Sinovoltaics. And also joining this webinar is Trikus de Roy, the Managing Director, and Niklas Weimar, our Chief Technology Officer.
Hello.
Our company Sinovoltaics is a technical compliance firm in the PV and ESS industry, best known for performing quality inspections and audits at the factories in Asia.
Sure.
The main issue we're focusing on today are defects that occur in solar cells and how to prevent those on a mass scale, with the objective to only have flawless solar modules in your PV projects. We're starting with how defects can be detected using EL imaging, and we will explain what solar cell defects you can expect to find at the PV factories. From there, we make the jump to our in-house developed software and explain how it can be used for the detection of defects on a mass scale. Then, to show you how the software works, Trikus is going to walk you through two real case studies, a case study of 36 megawatt and one of 68 megawatt. In total, we expect the presentation to take about 30 minutes, and then we have a Q&A session at the end. And we finalize the webinar with a very special offer. For those who develop large-scale PV projects, we can now offer some free trials. Trikus will explain you more about this at the end of the webinar. And some basic information. So the webinar will be recorded and everybody who signed up for the webinar will receive an email with the recording at the end. And during the webinar, you can ask questions in the chat. So if you have questions, you can put it in the chat and then we can answer it directly or later during the Q&A session. So before we dive into the case studies, we'll have a look at the EL imaging, what are microcracks, and the different type of microcracks that you can expect when you build PV projects. During this webinar, we speak a lot about microcracks, but in fact, there's many other type of defects that can be found when using EL imaging. For the sake of simplicity, we will just call it microcracks. The thing about microcracks is that they cannot be seen with the naked eye, but they can be made visible using electroluminescence imaging, or EL imaging. EL imaging is one of the key tests during the production. The EL imaging is performed at PV factories on all solar modules. However, factories review the images manually with the naked eye and defects can be easily overlooked. This is how modules usually can end up with cracks in your project. So we all know that large PV plants are built using 10,000 of connected solar modules, and those solar modules in turn consist of 100,000 of connected solar cells. For excellent performance, it's critical that all these connections are functional, so your generated electricity can flow without interruption. Microcracks inside solar cells are the cause of malfunctioning and inactive solar cells. Such defects can create resistance and can cause the power output of your solar modules to drop. Microcracks mostly occur during the manufacturing and can also occur later during the transport and installation. We also see that cracks can get worse in the field over time, and therefore the underperformance can also increase during time. Then, on the left, you can see the cover of our own EL standard. So when buying solar modules from a PV factory, it's always important to be aware of the quality standard that you agree to in the contract. So EL defects are listed in the factory's EL standard, but those factory EL standards are usually not that strict, which means that some defects are allowed to pass. So we recommend to implement your own EL standard, or we can help you to adjust the factory standard. This will directly raise the quality level of your modules, and most PV factories accept those requests. Now I will let Trikas go for the following slides.
Thank you, Benoit, and hello everyone. For those who don't know me, my name is Trikas Troy. So I will continue here and tell you a little bit more about our in-house developed software called SELMA, ELMES analysis. To start, let me tell you why we developed our own software for EL reviews. Because mass scale inspections at the factories, that's still something very special in the PV industry. Now, the thing is, most inspection companies, they only perform sampling at the factories. Let's say you order 10,000 solar modules. Most companies, they would only sample 125 or 200 pieces. With sampling, you get a general idea of the overall quality of a batch. But the reality is, and the disadvantage of sampling is that many defects, they go undetected, and they actually end up in your PV project. Okay, and we see it as our mission to reduce any of the risks for large-scale PV project as much as possible. So over 3 years ago, we thought there must be a better way to do this, and our CTO Niklas Weimann was here also on the call for the Q&A session. He decided together with our development team to create a software for this. So we're able to inspect all solar modules based on an EL analysis. There's over 15 different defects that it can detect. And as the software is self-learning, it's getting better and better as it processes more images. So we've been around with the company since 2009. So we have actually EL data with different types of defects for over 10 years. And the software is constantly being fed this new data. So it's constantly being improved. So even defects that may happen in the future, the software will pick that up pretty fast. And this way, it's now highly accurate. The way it works is once production starts, we go to the next slide actually, because it gives you a brief overview of the software. Now, once production starts, our team is usually present at the factory. We usually integrate this ELMES analysis into our inline inspections. And the way it works is we set up a data stream to our server inside the factory, and then high-resolution EL images are being uploaded. And while that's happening, the software starts analyzing, and defects are automatically marked. And this is happening on the fly, so we can keep up with high-speed production. Then, when any defects are detected, the serial numbers are then sent back to the factory where our team is present, and they then remove those modules from your shipment. Okay, so the result is that all the solar modules are quality checked before they leave the factory. Now, we put together 2 case studies. I'm going to show you so you have a real idea what it can mean for your projects. So this is the first case study. Very typical large-scale project, 36 megawatt at a tier 1 in mainland China. Mainstream technology, mono-PERC half-cut cells, 455 watt modules. And production was fairly recent, was Q1 this year. Now, if you look at results, on the right, you see the type of defects that the software has found. And you can see that the most common defect was single cracks. And single crack here is marked here in yellow. And then cross cracks, there's no image of that. And a cell piercing crack, it's a crack that goes from left to right to the cell. And then dendritic cracks, that's the one on the left here in red. A total of 2,880 pieces, we found cracks. And that accounts for 3.56%. That means that all these 2,880 pieces were replaced on site. And like Benoit mentioned, it's very important to realize that when you make such a strict selection of, okay, what is permitted, what defects are permitted and what not, it's very important to agree on a clear quality standard with the factory. But the defects you see here, typically, they should be replaced. So just a summary. So it's a tier 1, over 80,000 modules, 2,880 were replaced. 100% has been checked. And what's important after we do such an exercise and we replace those modules is that we're also in charge of overseeing the packing and the loading of the containers, because you really want to make sure that those 2,880 pieces, that they don't end up in your containers. So we make sure of this. Therefore, the EL reviews, they're typically part of an inline inspection. Okay. Just going to show you another case study. This is a factory in Vietnam. And we have a permanent team in Vietnam. And this is at one of the larger players in Vietnam. Most of these products, they leave for the USA market, but there's also European clients and Australian clients for the Vietnamese factories. Large modules, 540 watt bifacials. So 68.9 megawatts, in total over 127,000 modules, where we again do 100% inspection. Okay. What you see here is the most common defect here were solder faults. You see solder faults here, you see it here marked in green, and that means that the solder connections of the tap wire is not done properly. You get this shading effect, part of the cell. Okay. In most quality standards, that's not allowed. So in this case, we were able to replace those. Then again, single cracks, cross cracks, and cell piercing cracks are the most common ones. Cross cracks, here you see one in light blue. Typically, they get larger over time, and it can get worse to the point that they might create an active cell part, and that can degrade the performance in the long term. So for this project, we replaced 3,321 pieces, which is 2.6%. Okay, here a summary. Again, Tier 1 Vietnam, 127,680 pieces, and we replaced 3,321. Okay. What used to be the case with most inspection jobs is that if you have a 68 megawatt, maybe you would divide it into 13 or 14 batches of 5 megawatt each. And then for each batch, you would maybe test 125 pieces sampling. Okay. And then for each batch, you would decide, okay, how many, there's a certain AQL. You would say, okay, how many pieces have defects? And according to the AQL, you would decide, okay, 5 megawatt batch is a BESS or a fail. That's still what's happening a lot, but it doesn't help you as a PV project developer if you really want to make sure you have no defects in your PV park. Okay, by replacing these 3,321 pieces, you remove any serious cell inherent defects, including microcracks, from your shipment. Okay. That's it for the case study. We're going a bit faster than I expected. We're just 15 minutes in. We're already past the case studies. One thing that I don't know if anyone mentioned, but if you have any questions, please feel free to type them in the chat so that we can answer them at the end of the webinar. Okay. Next slide. Here are some of our references and some companies that see the value of mass scale inspections. You could say they're quality leaders in that sense that they remove 100% of the defects from their projects. And the next slide is the adoption by the factory. So we've been receiving very positive feedback over the years using our software at the factory. It's very transparent. Typically the process is, okay, a quality standard comes either from the buyer or from the factory. If it's a factory standard, sometimes we help the buyer to see if the standard is strict enough. Maybe there are some adjustments to the quality standard. And from there, we take that as a basis for the inspection. And all the major factories, they have adopted the software. They're open for it, and we're able to implement it successfully near the factories, at the factories in Asia. So not only in mainland China, but also at the factories in Vietnam, Taiwan, South Korea, at pretty much all the factories in Asia. Okay, so I'm already at my final slide here. So what we would like to offer you today is a free trial. So for this time, we're offering 100 megawatt of free trial for companies that are developing large-scale PV projects. Okay, so requirement is that you have to buy directly from the factories in Asia. Okay, if that's what you're doing, you can really benefit from this free trial. We give away maximum 10 megawatt review per company, and it doesn't matter from which factory you're buying in Asia. It can be any factory. It has to be a project this year, so we can really show you the results and really show you the benefits for your PV projects. So far, we had tremendous feedback from our clients. Many have no idea about what they're buying exactly, but this gives you full insights in the state of the solar modules. And of course, this is only one test. It's EL imaging, but it's one of the key tests you can perform. Aside from that, there's IV testing, there's the verification of raw materials, there's visual inspections, and so on. EL imaging is really a key test, and we believe that any developer of large-scale projects can benefit from the use of this software. Okay, that's the end of the presentation. that brings us to the Q&A session. Let me have a look what questions are there. And I see some interesting questions here. Our CTO Niklas Weimar, he's also here. He is actually been leading the development of this software. So who better to answer these questions than Niklas? So here's the first question. Nick, maybe you can come to the stage and answer this first question. It says microcracks. It's a question from David. He says microcracks lead to inactive cells, but manufacturers claim there is no influence to the output power. How to fight back?
Yeah, this is a good question. I mean, there's certainly first of all, the argument comes, of course, from the perspective of a standard where this is basically not enforced strictly, basically, and so if you would, for example, agree with the manufacturer to on a lax standard, so to say, I would find it quite challenging to fight back, so to say. I mean, this is about fighting back, or whatever you would call it. So it is actually very prudent to have a very good quality standard in place. Now, when it comes to arguing about this, actually, like the argument of why microcracks are basically, why they are perilous to the long-term success of your projects. There's not a given, but there's a potential risk, basically, for any cell or for any cracks in cells, basically to grow over a longer operational time. There is, your modules and the cells that are encapsulated within that module are laminated within that module. They're basically subjected to all kinds of environmental and mechanical stress forces outside in the open, in Mother Nature, so to say, over a long time. And of course, you want to reduce this kind of impact by, or the potential of this impact by very early on already get rid of modules with such cracks. If you have already some basic cracks already, they may just expand by these pressure forces over time. It's a potential risk, which is also in studies that we have seen also with companies that do analysis basic in fields. We have seen then that they would also grow over time. Not for all cracks. Again, it's not a given, but it's a high potential, and this is why you want to get rid of this. Regardless of the numbers of how many percent of cracks could potentially crack, but for each there's at least the potential there. So you want to basically start with a very clean batch, so to say, of modules in your project. And it also starts with a good standard. That makes fighting back actually easiest.
Yeah. All right. So there's quite a few more questions. I will just pick another one. Maybe I can answer this one. The question is, can Selma be used for production? For example, replace or jointly used during production? It is actually used during production. So we use the software from the moment the production start, and we use it throughout production. So the moment the actual EL imaging is performed on site at the factory, the data is uploaded to our server, and we review these EL images. So if you have, let's say, a 50 megawatt project, production is 25 days. It means that during those 25 days, we are continuously reviewing the EL images. Okay. Years ago, we would do this with manpower. So we used to have many people looking at big screens and looking for cracks. But because the volumes that we inspect and the project sizes have been going up over the years. So it's impossible to do it manually these days. So it's definitely performed during production. This is maybe a question, Nick, for you. The question is, what's the smallest size of microcracks that can be detected?
The smallest size, well, we are as capable as basically detecting these so-called smallish V-cracks that we would find now in MBB modules. So, and that's in the very, very smallish millimeter range. So we can fairly, you have these newer MBB modules which are somehow also more prone to so-called we call them MBB cracks actually, but these are like cracks at the soldering edges basically of the cell, and even these can be detected. So that's currently the smallest kind of a crack that you can actually find on such projects, and we can fairly well deal with that.
There's actually another question about this, Nick. So the question is, do you consider V microcracks, that's exactly what you're just mentioning, he's referring to Jinko tiling ribbon lines, a defect worth filtering out at a certain number?
There's different how you would call it, schools of thought about this, but let me be clear about this. Any kind of crack that you have could potentially grow over time. There's of course potential, but then you have also the other perspective basically for these new type of cracks, that they're so smallish, and it is quite an how to say, it's a question basically how perilous the impact is. Normally speaking, I mean, for this you would need to look at actually in the long term at projects basically, when these projects have been fairly recently now installed on the impact. So it is, and keep in mind this is a new technology also, or well, basically they come from new technologies which are even also in all honesty also very, very hard to manage actually also for factories, even though there have been many improvements made in this field. So I mean, with us, of course, you can filter them out. After all, it also depends on the criteria that you set for your project. Maybe it's a good way to put this. Yeah.
And of course, it all boils down to the quality standard that you agree with the factory, right? So
exactly.
If the factory is confident, it says, well, we can agree on the standard that such small V cracks are not allowed, our software can find them and we can replace those modules. But many factories now tend to be a bit more lenient when it comes to these very small cracks. So it's something to look at on a case-by-case basis, and it also depends on the factory. And so we are always willing to, be as strict as possible, but in the end, it's a cooperation between a buyer and a factory, and you also need to agree on reasonable requirements that can be executed, because don't forget, of course, factories, they produce on a very big scale, and so it needs to be realistic. But obviously we can detect those cracks, and if allowed, according to the standard, we can filter them out. Okay, let's have a look. Has the software analysis results been compared to human analysis to prove accuracy / reliability and so forth? Yeah, maybe I can answer this. Yes, it has been. So we actually, years ago, we actually did all the analysis manually. So we've been gradually switching to our software, and when when we find defects, the results are actually communicated with the factory, and the factory then has a look at those results, which is a human analysis, and then they tell us, okay, that's right, this is not according to the standard. So there's always the human factor involved, and yeah, data, all these results, they're if the software in the past would pick something up that was maybe not a defect, and that's immediately fed back to the software. So it has been continuously improving, and nowadays it's much more effective than a human analysis. Nick, maybe a question for you. Can the defects by microcracks too been detected by analyzing the electrical specs by flashing?
Yeah, this is an interesting question. I would say with limitations. So you could, for example, and we have had this actually in the past in some cases actually where we had to resort to how to say affirmative tools, so to say. Well, yes, before the software also. Basically, you could see on the IV curves basically of flashes. So if there's if the impact of the cracks is already, so to say, of microcracks, is already mirroring, so to say, in the electrical specs, you could actually see some kind, for example, on this IV curve, you would see some kind of like step pattern, for example, like stairs, a step pattern on a curve, like very minuscule, but you could see this basically, and this would point actually to the potential existence of such cracks. So so we had a few cases actually where we did this correlation. So it certainly exists, but I would deem this not as a sufficient exercise basically to do like an analysis on the mass scale, basically to be really sure that that the modules are free of cracks. For this purpose, I think this is then too weak of a tool basically. But it helps for correlation in some cases for sure. Yeah.
Okay. The presentation was a bit fast, but we have a ton of questions, so we can keep going like this for a while. Let me see. Commercial question. Do most manufacturers add a price premium for slightly stricter panel criteria acceptance standard? The answer is no. Most factories do not, unless you maybe go to the other extreme and impose a standard that really requires a double-digit percentage of modules to be replaced. Okay, and then it really becomes very intensive for factories. It really requires them much more manpower, and in that case, we've seen sometimes some price premiums, but 9 out of 10 times, no price premium. And actually, there's also quite some buyers that simply follow the factory standards, and there's still plenty to find and plenty to filter out. So question about PV projects in Indonesia. I'd like to know about your experience works for QA of solar projects for project in Indonesia. There's actually a nice PV factory in Indonesia, and we have been doing inspections there as well. It's a Suntech factory, and they mostly produce for the local and for the USA market. Okay, what else? This is Mikael. He's asking, can you change the pass fail criteria in the software? Use harsher criteria, for example. Nick?
Yeah, This can certainly be said. The software, after all, filters, detects and filters basically any defect, and then we can again apply, a so-called pass-unpass basically filter on this. So this is certainly doable. Yeah.
So here another interesting question. So the question is, should an importer of solar panels for each container after arrival should make these tests? Let me answer this, because it's actually a good question. Look, we're a testing company, right? So usually from our perspective is the more you test, the more certainty you have, right? Now, cracks, they occur during manufacturing, but they also happen during handling, okay? And you know, if you have a professional EPC, any handling damage can certainly be minimized. Yeah. What we see is that during transport, if you follow all the best practices in packing, there's actually very few damage done to solar modules. Now, there are exceptions, okay? If a module is transported by truck 600 kilometers over a bad road, sure, damage can be done. But the regular routes from, let's say, Shanghai to the main ports of Hamburg, Rotterdam, Antwerp, for instance, in Europe, very few cases of damage. So should you then do again test upon arrival? From our experience, if you already checked 100% at the factory, the best way to do it is to unpack the containers and directly install them. The reason for this is the following. Those modules have been 100% checked. There's a very small chance something happens during transport. Much better spend the testing money to look at your plan maybe in 1 or 2 or 5 years and run some tests to optimize performance. Now, what's going to happen if you do tests after the modules arrive? Someone will come on site, they will unpack the modules, they will test them, fine, you get some result. But don't underestimate that the handling of these modules can also create damage. Okay, so and if there's damage, then maybe the factory will say, well, maybe it's the testing company who caused it, right? And the testing company will say, well, it's probably the shipping. So you basically create a liability problem this way. So it's much easier to do 100% inspection at the factory and then be assured everything is in top shape, directly install it. That's my opinion. There's definitely other people with different opinions, but that's how we see how a lot of successful projects are done. Let me have a look what else. This is an interesting question. Nick, have a look. What is the most efficient and quick method to check for microcracks on panels of a large project that are already installed on site? So my quick answer is there's no efficient or quick method. Okay, but Nick, go ahead.
Yeah, I fully agree to this. It's yeah, so I sometimes actually I have this also with other colleagues in the industry. I have this discussion. Is actually yeah, it's quite a topic to basically what you look at here with this question is basically mass check on the modules for EL imaging. Now, what happens is basically the electroluminescence imaging needs to happen in a certain under certain conditions. So, for example, with the current technology available, right? So you need to either cover the modules or you need to do it at nighttime, basically to do EL imaging. For this, you need basically portable equipment. We actually have this. We actually also have been doing these kind of commissioning assessments But let me tell you, it's in all honesty, it's a very tedious task, especially when it comes also to to large sizes. You need to have a huge volume of equipment and a huge volume of manpower, basically, with the current technology available to do this. You have to power up the modules at nighttime, and then you have to basically go from module to module. You can also we have also special equipment to do whole of strings, but still, we talk about, for example, 100 megawatts, and then you end up weeks, probably months. There have been attempts to do this with drones. That question may also probably be in the back of the mind for this question, but it's also not very efficient at the moment. Also, when it comes to stability and holding patterns of this kind of device during flying and powering up all the whole swings, it's very tedious. There might be some solutions coming up in the future, but it will not be based on EL. And we still have to see if that it would enable us basically to detect microcracks. Maybe the fastest way to have at least some kind of a preliminary assessment is actually to do thermal imaging. You could not see the cracks themselves, but you could see at least impacts that come from those cracks, like, for example, hotspots. So when there's like enough resistance and heat build-up at the localized level in the cell, you could then detect it, and then you could go further down and then look at this. But on a mass scale, no. And and this is why basically we have quite a preemptive approach, and that's why we also are the factories doing that.
And underestimate the cost to do that. I mean, if you really have a field full of cracks and you're going to try to solve that on site, it's I mean, with most companies' equipment, I think they can test maybe 150 modules a night, like something like this. So then you have already a team with equipment going out at night, and then the question is, okay, how many pieces are you going to test? So these are inspections that can take many days, weeks, or even months, and it can be very easily prevented because you can filter them out at the factory automatically with software. So it can be troublesome if you have a field that is really affected. Another question: do microcracks are they more critical in frameless modules due to bending of the module because of wind load? I've seen quite some frameless modules that are actually passing all the mechanical load testing and the wind load criteria. I've seen frameless modules that are pretty much as strong as frame modules, unless you have a different take on that, Nick.
No, I fully agree. It's in the end, it all boils down to the overall design and choice of materials. Yeah. So that's fully agree with that point that Rico's made already.
Yeah, this is an interesting question, but maybe hard to answer. How do you quantitatively correlate critic parameters, i.e. size, length, etc., of micro defects to the lifetime of power loss of a module? Yeah, this is almost an academic question, right? Nick, I know you do a lot of research on this. Is there a simple answer to it?
Very simple answers. And since I have this discussion often, it's hard to say. There's just a lack of data. There is there's certain indications when it comes to, for example, certainly when it comes to positioning of the cracks and the malicious impact, and certainly also like location basically and shape. So you could probably correlate shape with size or length, but the long-term impact, so to say, I mean, there's very few data there. There's also very few research papers. If you look at this actually that have actually looked at this and compared this, I believe it will take probably many more years, probably talk about decades actually, that we have sufficient data, and then we can actually look into basically historical patterns of development of cracks and the impacts. And actually, it very much requires that you do some legwork in the beginning. That means basically look at the module, the state of the module at the very beginning. So otherwise you will never know how it degraded and what the impact was. So, and that's with that actually we also, with the work that we do, and we collect lots of these data, we also lay some kind of legwork, and actually also cooperating with academic institutions to add this to my point. Yeah.
Okay. Another good question. Manufacturers also analyze the EL results to apply their factory criteria. That's right. Is your added benefit that SALMA is more accurate or reliable to find more defects than the manufacturer would? Can you explain why the default manufacturer analysis is insufficient? Yeah, that's a very good point. There's two sides to this. Okay, so the first thing is that yes, factories, they have their own criteria. The first thing is to look at those criteria and see if they're strict enough. And it's not so much only about being strict. It's also about being complete. Because if a standard does not include a defect, that means that automatically that defect is not important and it will be passed, right? So the standard needs to be looked at. But let's say you follow a factory standard. The reality in the factory is that there's at least two moments in production where EL imaging is done. It's just before lamination, and it's after final assembly, so as a final quality check. Now the step just before lamination is a critical one, because if you find heavy cracks there, factory can still make repairs. Okay, and this is very common. During inline inspection, we also supervise this, and then we see that quite a percentage of modules can be repaired, so that in the end they will pass. Okay, so that's the first EL step. Now the final check, the factory performs EL imaging, and somebody is sitting there physically looking at these images. Okay, now there's a lot of variables that can influence the results. First of all, it's the human factor. There's somebody looking at a screen all day. It's very tedious. That person might take a break. So they're maybe not always on top of it. Second thing is the EL equipment calibrated? What's the resolution of the images they're looking at? So some factories have new equipment, some have old equipment. Do they set it at the most accurate settings? So sometimes there's somebody's checking them, but the resolution is very low, so they cannot possibly see much on these images. Okay, and of course there is the thing that for factories their yield is important. So why would you reject 1 or 2% of your modules if nobody's looking, right? So the question is if they will stick to the factory criteria. So that's our job, to make sure it's properly followed, to make sure that the standard that you agree on with the factories is really implemented. Another question. Flexible panels. How do you see the relationship between flexible panels and microcracks? Yes. Yeah, that's interesting. Most flexible panels are not suitable to be bended much, and so if you take those with semi-flexible IBC cells and you flex them 10 times and you would do an EL test, then there's a very good chance they're full of cracks. And so it really depends on the technology. I guess thin film technologies would be more suitable as a real flexible module. But most of these modules they can crack too. I don't know. I guess that's. I mean, we could go over all the different technologies of flexible modules, but most of them we see the cells can crack. Okay, another question. Oh, I need to put it up. How fast can the system be ready for a completely new assignment using different EL criteria? Are you now using your own criteria to evaluate, or can it be easily adjusted to different criteria? How fast the system can be trained for a new defect type model? Yeah, so the first thing is we can almost instantly switch to new criteria as long as the criteria are clear. Because we have teams at different factories at any moment. So we are using the software simultaneously for different criteria. So that's fairly easy for us. The software is ready for this. And then how fast the system can be trained for a new defect type model. It depends on how much data you have. Okay, so if you have a defect that comes up, and let's say you have a couple of dozen different images of those, that's already sufficient for the software to recognize it the next time. But then if we see that defect more and more, and we see hundreds and thousands of these, then the software learns about it, and it's completely integrated in the analysis. So it needs some images to understand it, and from there it's pretty much self-learning. Let me see. Nick, would you like to answer this question? It says in case study number 1, defects are mainly related with microcracks/cracks. How about the performance/accuracy of the system to evaluate defects related with gray value, like cold soldering, over soldering, cells efficiency mismatch?
Yeah, so our software can fairly deal with a variety of different kinds of cell inherent defects. Of course, the most prominent ones are usually the microcracks, and they're also the main subject of this webinar today. But after all, we have actually implemented detection for over 15 different types of defects that can be detected, and it includes basically, yeah, also a cell efficiency mismatch, that cells grid connect finger interruptions, then also like yeah, solder defects. So it broke the cells. So we can fairly deal with a large variety of defects. What happens is actually nowadays, Jacobs mentioned that we have an accumulation of an unspeakable amount of EL images from over 10 years. And of course, the type of defects that we would have seen over 10 years ago are nowadays more rare. We have, however, still when we started out, we still started to involve all these and cater to all these defects, not ruling out that at some point, you know, with new technology development, some of these now, I would call it extinct defects would pop up again. I mean, not fully extinct, but so some defects have over the years become fairly rare to be seen actually in EL images. Some have been new. I mean, we are just talking about like new, like these small MBB cracks, we call them. But we are constantly catering to this. So to make it short, yes, it can address a fair variety of different defects aside from microcracks. Actually, it's up to 15 at the moment.
There was a question by David, by the way. David, I believe I know which David this is. David, Nice to have you on the webinar. We should catch up one of these days. Another interesting question. He said, I understand you use the EL images from the flash test. It's actually not the, well, flash test, the flash test is also often the IV test, but let's call it the EL equipment made by the manufacturer at the factory. Have you considered the requirements that may be required of the EL imaging so to get the best images for your software to analyze? I refer also to the settings of the power source that energizes the module as well as the camera taking the images, since this combination of factors affects the quality and contrast of the EL and thus the capacity to identify certain defects, like weak and cold soldering. Yeah, I think that's a good question. Nick, would you like to?
Yeah, I can only confirm the perception, or basically confirm this assumption here. So there's we have also within our own EL standard that we offer. Yeah, so basically, like by many other default standards by project developers, you have actually their default requirements for resolution, basically, and image file size, and the reason for this is simply basically to set like a bottom line for the quality of images. So you would stipulate this in megapixels and also in file sizes. And now there's actually nowadays all the big makers, I would not say all of them, but the vast majority of them, they have very decent equipment in place to basically offer high-res and good quality non-blurry images, basically that enable also much easier detection. Maybe something to add to this. Actually, we have again I mentioned that we have collected many countless images over the past 10 years, and of course the quality of these images has been fairly different. And we started out by training, also by working on our own software with also lower quality images and blurry images. The very intention behind this is actually also to make our software really much ready for also the occasional instance where there is such offer or like provision of such bad quality images, and it can fairly recognize and detect and mark then cracks that would rather already be lost by the human eye, even with lots of labor attached to that by looking at the images. So yeah, we have requirements that we recommend. Many project developers also have. We can also deal with low requirements, but however, the better the image quality is, of course, the much easier also is to see the marking. I mean, yeah.
Okay, here's a question about the cost of using the software. Well, just to go back, we have a free trial. So if you're working on a project this year, certainly get in touch. We'll be very happy to demonstrate the software and help you with your project. Cost is it really depends on the size of your project. When you work on a project, leave us a message, and we'll ask you a number of questions. We'll set up a call, answer a number of questions, and then we can prepare an offer for you, and then you have full insight. But let me say, this is a really cost-effective way to assure the quality. It's yeah, there's no other way to really inspect 100% of the modules, and it's done by software, and it's done in a pretty fast way. There's still some more questions. One moment, I have to read them. Okay, Greg, you had some problems with the connection. Sorry about that. We'll read that. But Greg is asking for more information, and we'll certainly get in touch with you. Thank you for the interest. David is interested to know more about the quality of the EL images. He's asking the system for evaluation, does it work with critical major mining or with A, B, C, D? Most standards are working according to critical major minor, because this is how the factory works. So it's usually good to agree on a standard that the factory uses the same methodology. So you basically speak the same language. Yeah, MBJ, yeah, it's a bit of an older standard. We don't see it so much anymore. Comes by sometimes. So most standards, they are working with critical major minor. Okay, I believe we are pretty much through all the questions. If there's questions we haven't answered, we will get back to you by email. Thank you very much for attending. As mentioned, if you have worked on a project, feel free to get in touch. We'll be very glad to offer you a free trial, and we hope to be helping you with your next PV project. I hope that was very interesting for you, and we'll be very glad to see you again in one of the upcoming webinars. All right, bye for now. Bye-bye.
Good day, bye-bye.
Visit Sinovoltaics.com to learn more.